Okay, we're here with Eric Lerner from the Lawrenceville Plasma Fusion Research Center. Is that correct?
Well, we mainly go by the name LPP Fusion
Okay.
because we're no longer physically located in Lawrenceville, which is a town in New Jersey.
Okay.
So LPP Fusion is going to be more familiar to people.
Okay. And Eric has published a book by the name of Big Bang Never Happened and been studying and researching cosmology and astronomy for many decades. So we got him on the show today to try and find out what this black hole image represents and what the significance of it is, if anything. And then perhaps we'll wander onto some other themes. But bear in mind that both myself, Leon, and most of the people listening are relative laymen on the subject matter. So you'll do most of the talking and we'll just cross question you when something brings to mind. Yeah. So this black hole image that made world news a few weeks ago, what do you think the significance of it is?
Well, let me just correct one thing about myself is over the years, most of my research has been in the field of nuclear fusion. I've also done a lot of work in astrophysics, and we'll go into what the connection is between those two fields, which is important to what we're discussing.
Good.
Well, to begin with, obviously, the media have said this is an image of a black hole, period, ended. Now, there are a few things to understand about what this image is. First of all, this image is not a photograph. They don't claim it to be a photograph. Mm-hmm. It is a highly processed image because they are taking not images, but streams of data, just one-dimensional streams of data like you would get from a radio station, from several different radio telescopes, which are really big dishes, some of them many meters across, scattered around the world. And it's well known that you can put these data streams together and form an image. The problem is they have so few of these big stations. The image you form has a lot of ambiguities. So what they're actually doing is making a theoretical model and seeing whether they can, and they make a large number of different varieties of theoretical model by tweaking one aspect of their model or another. But these are all models of their theoretical black hole. And then they see which one can fit the data they've got best. And then they create an image based on that model. So it's quite indirect. That's point number one. Now, point number two, and this is what's probably of more interest to the average reader of the newspapers. Question is the object they're imaging definitely a black hole? A black hole is a really amazing, paradoxical object. A black hole is something that is so dense that no light can escape from it. And at its center, this can't be directly observed, but this is what's theorized, there's a point of infinite density, a singularity. Mm-hmm. Well, one thing that is really beyond debate among cosmologists, but they don't like to leak to the media, is that none of them believe that an actual black hole, as I just described it, can exist in the present day universe. And that's for a fundamental reason. A black hole is hypothesized on the basis of Einstein's general theory of relativity. Okay. The general theory of relativity predicts that as the gravitational field of an object increases, the rate of passage of time slows down. Now, here on Earth, the gravitational field is so weak that it takes very sensitive measurements to see that slowing down. But as an object approaches, we're talking about an object that's contracting towards this black hole state called a Schwarzschild singularity, the time that the object is experiencing slows down. As it gets closer and closer, the time slows down without limit. And therefore, it's unquestionable, because nobody disagrees with this, that the amount of time that it takes this black hole to cross that limit and to become this black hole, the time that it takes this object to become a black hole is infinite. And since nobody believes that any objects in the universe are of an infinite age, and since most conventional cosmologists, almost all of them, believe the universe itself has only existed for several billion years, there is no question that these objects cannot be black holes in the sense of this mysterious thing that has a singularity at its center. So that's point number one. Now, point number two, when people ask, well, how can you call them black holes? There are two answers given. One is, I think, completely scientific nonsense, which is people have said and people have written, oh, well, from our standpoint, it would take an infinite amount of time for this black hole to form. That's true. But if you hypothesize an observer who is actually falling with the black hole of the object as it forms, then their time will slow down, and this infinite time that we would observe would seem like a finite time to them, to this observer, and they would observe the formation of a black hole. So it's perfectly mathematically appropriate to say, oh, they're a black hole. Well, that's pretty much nonsense. First of all, this observer couldn't exist. Any real observer would be torn apart by the enormous forces in the formation of this object. And second of all, we're still talking about something that can't be observed by us. Now, science is about observations that we can predict. And it's about that for a very good reason, because that's what makes science useful. If you understand aerodynamics, you can predict that an airplane designed in a certain way will stay in the air.
Okay, but
so that is quite invalid. So let me break there for questions, and then I'll get to another reply they have.
Yeah. So the process towards a black hole, let me just make sure I understood part of it at least. The process towards what they would call a black hole, you are saying they believe also would require infinite time to develop. But what about
That's right.
before that infinite time? What would exist before that if this process of collapse of space-time, is that right?
Right.
What would occur before that, and could we be observing a process that would lead to such a thing?
Right. That's the more valid answer. The other answer they give is, well, very soon, very early in this process, let's assume that there's nothing resisting this collapse. And that's a big assumption, as I'll get into. Then the collapse would proceed, the initial part of the collapse would proceed pretty rapidly, and not within billions of years, but within a very short time, months. There would be so little difference between this asymptotically collapsing object and a black hole that we wouldn't be able to observe the difference. In other words, that light would be, the energy of light would be more and more shifted to the red end of the spectrum, because light with longer wavelengths has less energy. And eventually, not a single photon would be escaping. It would, be one photon every year, then one photon every decade, one photon every century. So observationally, it would look pretty much like what a black hole does. Now, it would be a lot less paradoxical object because it wouldn't have the singularity at the center. It would still, and it wouldn't have the event horizon from which nothing could escape. But it would look pretty much like what they describe a black hole is. So I described this object as an almost black hole, or as an ABH. So the question really becomes, are we looking with M87, with these images, at an almost black hole, something that's asymptotically close to a black hole?
And what's your view of that? I mean, is it something that is verifying the theoretical framework that they've put together to suggest the existence of black holes, or to verify the existence of black holes, or is it something totally different? What's your view on that?
I think it certainly could be something that's significantly different. You have to ask, how could such an object form? Now, in space, any compressed object, including, like, for example, our own sun or any star, in order to form, it has to get rid of angular momentum. So if you remember back to your high school physics and the little skater who pulls in their arms, you see this at any skating exhibition, and they spin faster and faster. That's because the amount of spin, the angular momentum, is conserved. If an object doesn't get rid of angular momentum, it will spin faster and faster as it contracts until its centrifugal force balances gravitation and it doesn't contract anymore. For example, our solar system, the Earth and the other planets are not going to fall into the sun. The solar system is not going to contract because the centrifugal force of the planets in their orbits is balancing the attraction of the sun's gravitation. Now, how do we get contracted objects like stars? There's only one way to get rid of angular momentum, and that's through electromagnetic forces. Electromagnetic forces, the same forces that drive an electric motor here on Earth, they can transfer angular momentum. So what happens is that as a star or any object which consists of plasma, that's electrically conducting gas, as that contracts, the magnetic fields build up. And if you have a disk spinning in a magnetic field, that's a disk generator, which was invented 200 years ago by Faraday. Disk generator generates electric fields. And if the electric fields flow out along the axis, so they're flowing inward and then out along the axis, then the magnetic field gets stronger and stronger, the electric fields get stronger and stronger, and a force slows the object down. So the spin, the kinetic energy, is translated to electrical energy, and the angular momentum is carried away. All right. Well, if we look at this process of creation of magnetic fields and the elimination of angular momentum in the context of these massive objects, like the one at the heart of M87, whose gravitational fields can contain velocities that approach the speed of light, we know that the magnetic fields must also be approaching comparable strengths with the gravitational field. So we have to be able to study these things, taking into account both the gravitational and the magnetic field. Now, cosmologists do. The problem is they're using a wrong approximation. All of these images are based on models that use what they call GRMHD. Now, that's a pretty long abbreviation. It stands for General Relativistic Magnetohydrodynamics. MHD is magnetohydrodynamics. What's that? That's an approximation, an easy way to calculate approximately Maxwell's equations as they apply to plasmas. The problem is it's the wrong approximation. Now, Hannes Alfvén, who won the Nobel Prize in Physics back in 1970 for the development of the MHD approximation, many times, including in his Nobel Prize address, said this approximation is being misapplied to cosmic plasmas, that it absolutely gives the wrong answer. The reason is a little complicated, but I think comprehensible. The reason is that Alfvén developed this approximation while he was studying plasma in the sun, which is very dense plasma. If you go to much less dense plasmas, like that in the solar system, in galaxies, and in M87, you have plasmas that are not isotropic. They don't have properties that are the same in all directions, which is what MHD assumes. Instead, they have very different properties along the magnetic field lines rather than across. And that's because any charged particle experiences forces that cause it to gyrate along the direction of the magnetic field. The direction of the magnetic field we call a magnetic field line. The line doesn't exist, it's imaginary, but the direction of the field certainly exists. So if the rate at which this electron or ion circles around the field line is much faster than the rate that it encounters collisions with other particles, it becomes trapped in that direction, or scientifically, the resistance in that direction, the conductivity in that direction is much higher than the conductivity across the line. If you instead say with MHD, you use MHD, that these conductivity is the same in both directions, you get a totally wrong answer. Now, why do people use MHD? Well, for very good reason. It makes the calculations much, much easier. It's much easier to make a program, orders of magnitude easier to make a program that uses the MHD approximation than one that uses a more accurate, more detailed representation of Maxwell's famous equations. Maxwell's equations are very easy to write down. They fit on a t-shirt, but they are not easy to solve, even for a computer. So that's why people are using MHD, but it gives them the wrong answer.
So did you go away and read the papers that published on this MH or M87? And the other question I was going to ask was, what age are they giving to this then? If you're saying it would take infinite time to form a black hole, what age are they giving to it? What age do they think it's got?
Well, I think that most most, they think that basically these objects form at the time the galaxy forms. So that would be a number of billion of years ago. I don't know exactly how old they estimate M87 to be.
Mm-hmm.
On the other hand, as visible objects, it's generally agreed these are relatively transient objects being visible for millions of years at a time, unless you're very close to them. The theory being that well, in their theory, they have to have a supply of gas falling into them, plasma falling into them. I would say it's more that they have to have some source, a transient source of electric current supplying them. And this gets into the question of why does this theory really make a difference? The theory makes a difference is because if you use the correct analysis, which Alfvén did, what happens is, and this has been checked by observations both at the level of the laboratory and the level of the solar system, what happens is plasma's filament. So the currents are drawn together by the pinch effect, which under another name was also discovered 200 years ago by Faraday, which is that currents moving in the same direction attract each other. So you have filaments created everywhere. Now the filaments mean that the magnetic field, the currents can move through the plasma in this disk generator more efficiently. And they start to apply less and less force, and they start to become less and less efficient at deriving angular momentum. So if you do the calculations, the predictions from what actually works, what we can show works in observation, the process of contraction is going to slow down before you reach the almost black hole state. You're going to have something that is still a very energetic object, maybe with velocities moving 1/3 or 1/2 the speed of light, but with a balance between magnetic forces and gravitational forces and rotation. And way back when J. Robert Oppenheimer published the first paper in the 1930s predicting the process of gravitational collapse, he said this process can be balanced by other forces, including centrifugal force, rotation. So if you can't get all the angular momentum out of this object, then you're going to find a stable object short of this almost black hole. And that fits the observations we have if we are looking at this object in M87 from approximately along the axis. Because if it's spinning, then, and if it's in the shape that we think it would be from observations of smaller objects, then what you have is a sort of donut-like object, physically donut-like, in which the matter is streaming towards us on the outside and away from us on the inside. And because relativity says that objects going towards us appear to be brighter, objects going away from us appear to be dimmer, that would get you to something very similar to what we see. The important point here is that we know from the equations of Maxwell and from plasma physics that electromagnetic processes look very much the same at different scales. so we can see electromagnetic processes that form these little plasmoids, which are self-contained plasma blobs, even at the level of our laboratory. We are using a device that produces plasmoids that are tiny, that are hundreds of microns across and last billionths of a second, because the time and the scale linearly. And we see with our satellites, with the astronomical satellites, that in a solar flare, these huge explosions on the sun that sometimes interfere with our communications, we see the formation of these same plasmoids. Now, the difference is that on the scale of the sun and on the scale of the laboratory, gravitational fields, which are different on large scales than on small scales, different in strength, they don't matter. So on these very large scales, like M87, gravity is equal in strength to magnetism, and that makes these objects more powerful, more energetic than the objects that we're studying, but not by many orders of magnitude. The objects we're studying, these plasmoids in the sun and in our laboratory, have typical velocities about 1/30th the speed of light, 3% the speed of light. The object that we're looking at M87 has typical velocities that we're observing of perhaps 1/3 or 1/2 the speed of light. So typical velocities may be 10 times more than the plasmoids we look at that have no gravitational fields. But that means we can use the objects we observe in the laboratory and in the solar system, where we have, in situ, what we call on the spot data, and that we can use to understand these distant quasars. And as a matter of fact, our work in this very small fusion device, the dense plasma focus, actually started from my efforts more than 30 years ago to use the little plasmoids that we produce in the laboratory as a model for quasars, which are the sort of generic term for these very energetic objects in space, of which M87 is actually a reasonably small example. And I found that you could make quantitative predictions based on this model that helped us to develop further this fusion device, which is called the plasma focus.
In your opinion, what is the reason why they're trying to find these black holes, why they're creating models that allow them to, if you like, image their own thoughts, if you like? What's behind it, and what is basically, what is scientific method? What's wrong with the method they're using?
Well, I think that first of all, there's a sort of bias in cosmology that gravitation and general relativity are the dominant forces that you can use to understand cosmology and objects at the large scale. And, it's not that they completely neglect electromagnetic forces, but this is secondary. It's sort of flavoring in the soup, while the real soup, the meat of the soup, is gravitation. Now, that's part of a general sociological, ideological problem, is that for years, cosmology has been dominated by theoreticians who start with mathematical models, including models that are easy to calculate, and try to fit observations into that. And The reason why I say this is sociological, if you look at cosmology, if you look at the papers published in cosmology, and right now there are thousands of them published each year, you find that for every paper that reports new observations, there might be dozens of papers that are purely theoretical, that come from computers and from people's ideas. Now, that's very unusual for science. Most scientific fields, you have to have a lot of experiment and observation. And on that basis, a relatively smaller number of theoretical scientists, some of which who might be doing the observations and experiments themselves, try to understand that data and make predictions on it. It's almost like a feeding chain, a feeding pyramid. Many experimentalists producing the data, few theoreticians sort of feeding on the data. I don't want to imply theoreticians are like carnivores. But anyway, so that means in most scientific fields, although there's always a tension between theoretical and experimental science, the experimentalists, the people getting the observations, form the bulk of the field, and they have the greatest influence on it. In cosmology, that's turned on its head. The vast majority of cosmologists do not produce observations, they produce theory. So that means if the observers, the people who are actually taking data from these big satellites, from our huge telescopes, come up with things that contradict the theories, they're heavily outnumbered. The theoreticians can really beat them down and say, well, you know, this doesn't fit our theory. Go back to your telescope and get us new data. It's not just numbers. The control of cosmology is also very different. The control of funding in cosmology is very different than the control of funding in most fields of science. Most fields of science, because they are closely connected with technology, with things that are useful to people, either in the medical sciences or the physical sciences, there are many sources of funding. There are many governmental sources, there are many private sources. Cosmology, where the link with technology that used to exist has now been broken, you have only one or two in most countries committees. Like in the United States, we have an NSF committee and a NASA committee, and that funds almost all the science. And those committees are dominated almost 100% by theoreticians who have invested their entire career in a small set of theories, which is heavily weighted towards the idea gravitation dominates, that leads to black holes and the Big Bang. So you've basically got a sociological system of funding that reinforces an ideological bias towards theoretical calculations dominating over observation. And that's not the way to produce good science. The way to produce good science, and we have a history of that in the field of astrophysics, is linking observations on the large scale that we get from distant objects with observations we make in the laboratory, and using that knowledge for practical development of technology. For example, in my field, fusion energy potentially is an ideal energy source that can completely replace fossil fuels. The very process of fusion was discovered in the 1930s by Hans Bethe by studying what could possibly be the source of energy for the sun. And he could make that study based on experiments that had been done in the laboratory about nuclear reactions, about the equivalence of matter and energy, about the masses of various atomic nuclei. It was that link between laboratory experiment and astrophysical observations that allowed us to come to the idea that fusion is the energy source that drives the universe, that powers the stars, and that we can use it here on Earth. Now, unfortunately, the only way fusion reactions have been used practically on Earth has been in the development of thermonuclear weapons. But there is a significant effort to develop fusion as an energy source. And we think that by studying how plasmas operate in the wild, as it were, in the cosmos, we've developed a much faster route to fusion and a much cheaper route. So we're working on a machine that fits in a room smaller than the room I'm sitting in at our home office, a room a dozen feet on a side, not a giant tokamak, which is thousands and thousands of tons in weight. So going back to a approach to cosmic science that links it to science here on Earth can have very concrete and large consequences for what our life here is on Earth and our development of technology.
A couple of final questions then. Firstly, how does this, or is this theoretical framework that you're outlining to analyze what the observations they're making are, or the Big Bang, not the Big Bang, the black hole that they claim to have observed, is that connected in any way to the theoretical standpoint that people take in relation to this idea of the Big Bang? And last time we spoke was quite a few years ago. You were talking about objects in space that have been observed that are older than the time frame set by the Big Bang. Is there any advance on that? And what are the oldest objects that we can observe? And then, what's the other one? And then your experiments in attempting to produce fusion, have you made any progress? Where are we with that?
All right. Well, that's a long kettle. That's a big kettle of fish.
With short 10 minutes.
On the Big Bang, very briefly. The Big Bang theory right now is a much worse example than the whole black hole question of the improper dominance of theory over observation. What you have with the Big Bang theory is that this is a theory that has made terrible predictions. Predictions, you look at the Latin of the word, means speaking before. A prediction means before an observation, you predict what that observation is. Every time in the literature that Big Bang theorists have made a prediction, and then observations have come in after that prediction, the prediction has been wrong, way off. What happens is they then change the theory, make it more complex, and they say, oh, well, we can explain the observations we already have in hand by adding this new ingredient. So the ingredients that have been added was, for one thing, the whole idea of inflation. There's no evidence that any such thing, inflation field, exists. You've never observed it in the lab. It's almost impossible to observe it anywhere. Dark matter, that should be observable in the lab. It's called non-baryonic matter. They've used tons of money to have very sensitive experiments And each of those experiments has said no dark matter. Just last night, I was reading a paper that said the one experiment that called DAMA that maybe produced some evidence that there was dark matter, they replicated this on a larger scale, and they said that experiment is definitely wrong. That to a high level of sensitivity, there is no dark matter observable here on Earth, and there should be. Then they added dark energy. Again, no evidence on Earth or anywhere else that dark energy exists. It's just a fudge factor to make the theory meet observations that have already been had. Now, even with all of these ingredients, all these fudge factors, and I haven't mentioned all of them, the prediction of the rate of expansion of the universe, which comes from observations they've made of the cosmic microwave background, is significantly way off from the observations of the redshift, which is based on observations of supernova. So now, every day I'm reading, literally every day, half a dozen titles saying, oh, we have to add variability to dark energy. We have to have new forms of dark energy, 3 forms of dark energy, vanilla, chocolate, pistachio. It's just totally getting out of hand. By any criterion of scientific validity, we should have rejected the Big Bang Theory decades ago, especially since we have in the published literature theories based on existing physics that hypothesize, that have predicted all of these observations correctly in advance and do not include the hypothesis that the universe came into existence 13 billion years ago as a hot, dense ball of matter. So this theory really should be rejected.
So what are the oldest objects that have been observed now? I mean, that we know would contradict an argument.
The easiest thing to look at is, for example, stars in our own galaxy. So stars in our own galaxy have been observed because the theory of evolution of stars is pretty well developed on the basis of the nuclear physics we know here on Earth. So stars in our galaxy are certainly at least 14, 15 billion years old. There are some claims that I just read again yesterday, up to 20 billion. These new observations people are worried about, cosmologists are worried about, has reduced the age of the universe, quote unquote, from 13.8 billion down to 12.5 billion. So there's no question at all that there are hundreds or thousands or millions of stars that we've already observed that are older than this new estimate of the age of the universe. If you look on larger scales, galaxies, clusters of galaxies, superclusters of galaxies, and you figure out how long could have these objects taken to form, you get up to much larger numbers, hundreds of billions of years. So at all scales, from stars, which are relatively small on the universal scale, up to the largest objects we can observe, clusters of galaxies, the time allowed by this Big Bang Theory is much too short.
Okay, and how far have you got with producing fusion?
Well, we're just about. I'm hoping tomorrow, one never knows, that we're going to have a series of experiments with new electrodes, beryllium electrodes, that will much more accurately mimic the plasmas that we see in space. The problem that we've been having in the past is that the energies we concentrate are so great that parts of the electrode vaporize and enter the plasma. when we were using tungsten electrodes or earlier copper electrodes, that creates a plasma that is heavily contaminated with these heavy elements. So that doesn't look like the plasma in space, which is overwhelmingly nothing but hydrogen and helium. All the elements that we're made out of here on Earth are tiny impurities, 1 part in 10,000, 1 part in 1,000 in cosmic plasmas. Beryllium is itself a very light element. It only has 4 nuclear charges. So with beryllium electrodes, we think we're going to get a much better approximation to the plasmas we've been studying in space, and we think we'll get a lot more fusion. So we're going to see very soon.
Okay, I think that wraps it up. There's plenty for people to try and get their heads around and do research on there. Thanks very much for that. We'll be in touch again relatively soon about.
Okay, and can we put in a brief plug for the fact that if you go to LPP Fusion, you can also find our own video we've made on the subject of the black hole image.
Yep. What's the website address?
The website address is lppfusion.com. Okay? Hello?
I'll read them out to you when I see them. Here's one. Okay, here's one. Can you ask him what he thinks about Hindu scientists who said ancient India had plasma and nuclear radiation technology? It was at a science conference in India. Any idea?
Yeah, I mean, this is part of Hindu nationalist ideology. It's essentially equivalent to in the United States and UK white supremacist. It says, it's the ideology the Hindus are superior to other people, specifically to Muslims who are also living in the Indian subcontinent. It's nonsense. I mean, there's no evidence for this, and it doesn't really make a lot of sense. I mean, it's well known historically, and I don't think that anybody denies it in India. The ancient Hindu kingdoms were conquered by the Mughal Empire, by the Muslims. How could that happen if they had nuclear weapons and jet fighter planes? The Mughals were fighting with swords. So, I mean, this is like other supremacist, racist garbage that has been developed over the course of from the late 19th century to the 20th century, trying to divide one people against another. And the interests served are always the people with the wealth. What you have is the ancient art of picking somebody's pocket. If you want to pick somebody's pocket, you divert their attention, and then you pick their pocket with the other hand. So all of these ideologies are about saying, we, the billionaire class, are not your enemies, even though we've stolen trillions from you. And in India, we make you work for starvation wages. No, your enemies are some scapegoat over here, in this case, the Muslims. But in many cases, the Muslims are the scapegoat of choice, but obviously for Muslim populations, there's other scapegoats, Christians, and so on.
Yeah. So one other question here.
And obviously in the United States, we have Latino immigrants as the enemy. This is all about divide and rule. Okay. It has nothing to do with science.
We got one other question here, which is, can you ask him why scientists change their view from static universe to expanding universe?
Well, what happened historically is that at the beginning of the 20th century, there was no general thought that the universe had a beginning in time. When the Hubble relation was discovered, which was a clear observational relation between the distance of an object and a redshift, Hubble himself did not think that indicated expansion. It didn't indicate that this was a Doppler redshift. It indicated to Hubble that it was a redshift from some unknown phenomenon. Lemaitre took over this observation, put it together with his early Big Bang hypothesis, which was that the universe began as a single nucleus that broke apart by nuclear explosion, and said, well, this is evidence that the universe is expanding. At the time, most scientists didn't accept it. Einstein initially didn't accept it. But then people couldn't find another explanation for this redshift. And there was, Einstein decided that a stable universe could only be created with this cosmological constant. And therefore, there was beginning to be a shift by World War II of, the dozen or so people who were studying this, maybe the universe is expanding. The big shift came with the popularization of the Big Bang concept by George Gamow, who made the analogy between the explosion of the atomic weapons and the Big Bang creating all the elements. This turned out to be totally wrong. The Big Bang did not create the elements, and no astrophysicist thinks that today. Most of the elements that we're consisting of were created by nuclear reactions in stars. But there was a complicated process in which the coherence of the Big Bang story with, for example, Christian theology of the creation of the universe and other ideological trends, which I describe in my book, The Big Bang Never Happened, still available on Amazon and elsewhere, to make this the dominant approach. So it was a process over decades. Also, I want to emphasize the difference between the Big Bang and other approaches to cosmology does not have to be the idea that in one case the universe is evolving from the Big Bang, in the other case it's static. You can have evolution without the expansion of space. Here on Earth, we have plenty of evolution. The Earth has changed enormously over its life of 4 billion years, but obviously the Earth is not physically expanding. Different processes have caused it to evolve. And everywhere we see in the universe, we see a process of evolution, always accelerating, but never anything in which that's necessarily linked to expansion.
Okay, thanks very much, Eric. I'm sure that's given plenty of people lots of things to think about, and we'll post it up and link it into the question about the black holes, recently the discussion on the black holes. So thanks very much, yeah. Sorry about the last couple of weeks, whenever that was, a few weeks ago when it all messed up.
Okay.
Now at least.
No problem. It's good that we got it done. So and how will this be visible?
It's already visible on YouTube. People are watching it now.
Okay, but I mean, what's the URL and all that? How do I?
Anything else? We'll send you the link to the actual.
Okay, we'll put it on our, and that will be permanently archived.
There's one more question we're going to take. Yeah, one more question someone wanted to ask.
Someone wanted to know your views on the multiverse.
Excuse me for a second.
Views.
Excuse me. Ivy, could you please stop printing?
It's
Sorry.
It doesn't sound very loud here.
Working office.
Someone wanted to know your views on the multiverse. I think that's from Stephen Hawking, isn't it? Or who's it from?
Right. I mean, the multiverse again comes from this incorrect, unscientific method. I can't call it scientific method because it's not the scientific method. Scientific method involves predictions about observations we can make. The multiverse theory, which hypothesizes other universes that we can't observe, it's not a scientific hypothesis. It's not testable. So it's not science. When you make statements that cannot be tested, either confirmed or falsified by observations that we make in the future, it's not testable. And it's I want to emphasize, it's the question, the usefulness of science is it predicts things that we can observe later. Now, we may be observing them about events that have happened long in advance. If I make a prediction that, I've dug up an animal, a skeleton that looks like this, and I've dug up another skeleton that looks like this, and I predict that eventually I'm going to dig up a skeleton that looks something intermediate. That's a prediction. If you dig up that skeleton, that's a confirmation of your prediction, even though obviously these animals died hundreds of millions of years ago. So the key thing is prediction, subsequent observation, and then using that knowledge to advance technology. That's the cycle of science. Multiverse, it's not a scientific hypothesis.
Okay, thanks very much. It's been a pleasure.
Okay, thanks a lot.
Thanks, see you.
Take care, bye.
Peace. We are COE viewers. Respect for everybody that logged on. Man's gonna try to set up a show next Monday to do with some political discussions still in Jamaica. We're gonna get one professor on from Canada to talk about Edward Seaga and the CIA, crack cocaine, government business, all of that, you get me, sir? Make sure you log on, look out for that next Monday coming up, you get me? But yeah, we out now still. Peace to Eric. See you next time.
Okay, thanks.